Hi. Today's discussion will focus on bullets traveling above the speed of sound. This is also known as the bullet bow shockwave. In this video, note the shockwave that appears after the fourth shot is fired. Analyzing this system, there are three important parameters that lead to the shockwave. The first of these, which the other two will relate to, is the speed of sound. The speed of sound is a standard number in air, but this value is also related to the density of the air and the pressure. Therefore, it will have a different value in different fluids. In this analysis, air will be the fluid in consideration. Applying the continuity equation to a fluid flow through a control volume, this is the resulting equation, which is also dependent upon the surface area, a speed c minus dv, a pressure p plus dp, and a density rho plus d rho. After rearrangement and the consideration that d rho times dv is smaller than the other terms in consideration, the equation simplifies to rho dv equals c d rho. Through the application of linear momentum, the third equation is derived. By elimination of the higher order terms in this equation, a simple equation of rho dv equals d rho over c. Finally, by combining the continuity equation and linear momentum, we arrive at c equals the square root of dp over d rho, where c is now the speed of sound. One could also approach derivation of the speed of sound via the conservation of energy and arrive at the same result. We will not get into this in this video. The second property to be considered is the Doppler effect. It comes into play when an object begins to move. The sound waves are obscured from the standard emission of the sound wave. The wavefront gets pushed backwards closer to the location of emission and continues up until a certain point where the object is moving as fast as the speed of sound. At this point, the sound cannot travel in front of the object, as the object and sound will now be in unison. Once the speed exceeds that of the speed of sound, the sound of the object will not be heard until after the object passes a standard reference point. In application to a bullet, the bullet will have passed a stationary observer once the sound wave reaches the individual. This image displays this property as the object remains in front of the sound waves and will therefore reach the observer after the object's passing. The final property to be discussed is Mach number. This value is simply a ratio of the speed of the object divided by the speed of sound for a particular fluid. Objects traveling above the speed of sound tend to generate a sonic boom. This boom is a result of the air in front of the object being compressed, as the molecules of air cannot escape the object's travel above the speed of sound. A typical example of this is fighter jets. This same concept applies to bullets traveling above the speed of sound. Typically, this sound is masked by the loud bang of a gun, but if the sound of the gun were muzzled, the bullet still travels above the speed of sound, and therefore there will still be a sonic boom that can be heard by observers of the bullet. After the analysis of bullet velocity, it has been concluded that the average bullet travels faster than the speed of sound, and thus compresses the air in front of it. Therefore, it will generate a sonic boom, which for the most part can be heard as the bullet exits the barrel and continues during the bullet's flight above the speed of sound. In summary, this can be considered bullet bow shockwave.